Greetings to us all. We are going to finish up our discussion about creating confidence intervals, and we're going to be continuing our discussion about constructing one for the mean, mu. So when our conditions for inference are satisfied, remember we have those three conditions, the sampling distribution for x bar has a roughly normal condition. Because we don't know sigma, remember, we don't know this population standard deviation. We're going to estimate it with the sample standard deviation Sx. So the standard error of the mean is the sample standard deviation divided by the square root of n, where Sx is that sample standard deviation, and it describes how far x bar will be from mu on average in repeated simple random samples of size n. To construct our confidence interval, guess what, guys? It's not that different from constructing them for proportions. We go through the same set of things. Replace the standard deviation of x bar by its standard error in the formula for the one sample z interval for a population mean. Use the critical values from the t-distribution. Remember, we're using t now instead of z, with n-1 degrees of freedom in place of the critical z values. That is, we're going to use this formula, statistic plus or minus critical value times standard deviation of statistic. That's what we have right here. The one sample t interval for a population mean is similar both in reasoning and computational detail to our one sample z interval for a proportion. We have to verify three conditions before we can estimate a population mean. We have to make sure that we're random. The data must come from a random sample of size n. Our population must have a normal distribution, or the sample size must be large. That's our normal condition. N has to be greater than or equal to 30 if we can't verify that our population is normal. The method for calculating our confidence interval assumes that individual observations are independent. If calculations are sampled with replacement, we should check the 10% condition to make sure that the sample size is no more than 1/10 of the population size. So putting it all together, here is the one sample t interval for a population mean. Choose an SRS of size n from our population having an unknown mean. Confidence interval for mu can be found using this formula. T star is our critical value for the t sub n-1 distribution. Remember, n-1 is the degrees of freedom. And we will use this interval only when the population is normal or the sample size is large, and the population is at least 10 times as large as the sample. So let's do an example. We're going to look at TVs, some video terminals. The tension on the mesh of fine wires that lies beneath the surface of the viewing screen, too much tension will tear the mesh, and too little will allow wrinkles. So there's this web of wires behind a viewing screen, and they have to be held at the right amount of tension, the right amount of stress on those wires. So the tension is measured by an electrical device which reads in millivolts, MV. Some variation is inherent in the production process. Some variation will always be there. Here are the tension readings from a random sample of 20 screens from a single day's production right here. We want to construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day so that we can put on the box for this view screen that the tension will be this amount. And we want to make that claim fairly certain. So we're going to run through the 4-step process. Why don't you pause the video right now and get these data values put into your graphing calculator, because we're going to use that pretty extensively in this example to help us through. So we state the problem. We want to estimate the true mean of all video terminals at a 90% confidence interval. Our plan is that if the conditions are met, we should use a 1-sample t interval to estimate the mean. So if the conditions are met, well, the conditions are random sample, normal population, and independence. So random sample, we're told that the data comes from a random sample. Done. Easy peasy. Since the sample size is small, n is only 20, we can't use the large sample here. So we have to check whether or not the population distribution is normal. So we're going to look at the sample data in just a second. Our last condition for independence, because we're sampling without replacement, we must check the 10% condition, and it's reasonable to assume that at least 200 video terminals were produced that day. 10 times 20, 10 times our sample size is 200. So we can confidently say that these samples are independent of each other. So let's go to our calculator. We need to check whether or not our distribution is normal. So here's our data. I'm going to insert a data and statistics page, and let's look at a dot plot. Doesn't look like there are any outliers. If we look at a box plot, it looks fairly symmetric. And if we look at a normal probability plot, here's an important one. Back in chapter 2, when we were looking at the idea of a normal distribution, we looked at this normal probability plot, and if this normal probability plot is roughly linear, it's reasonable to assume that the population was normal. If this followed a pattern that wasn't linear, then we would say that it's not a normal distribution. If these dots made a nice curve like this, or it gave a parabolic shape, or it went up, down, up, down, up, down, if it wasn't linear overall, we wouldn't be able to say that this is normal. So because we have these 3 pieces of evidence, we have the normal probability plot showing a linear relationship between z-score and sample value, because we have a box plot showing roughly symmetric distribution, and because we have a dot plot showing us no real clear outliers, we can, with a reasonable amount of confidence, say that our data is coming from a normal population. Are we 100% sure about that? No. But we have sufficient evidence to say that it did come from a normally distributed population. Okay, so now we have to do our calculations. What do we need? Well, we need the mean of our data. We need the standard deviation of our data. So let's go back to our data table, and I'm going to calculate that. Statistics, stat calculations, one variable stats, number of lists is 1. My data is in list A. I'm going to put my results in list B. That's good. So here's X bar, and here is my standard deviation. So we have mean, we have standard deviation, we know n is 20. What are we missing? Well, we're missing our t-score. We're missing that value for t. We can use our table right here, but I'm going to show us how to use the calculator to do this. So I'm going to go to a calculator page. I'm going to go menu, probability, distributions, inverse t. Look at that. So the area, remember, when we use the calculator, we're putting in the area of the tail. So since we're a 90% confidence interval, that means that each tail would be 5%. Our degrees of freedom, since the sample size is 20, is 19. So here is our t-score. Our t-score, remember, we're going to count it as being positive. So I'm going to take the opposite of our answer, and I'm going to store that as t. So what do we do? Well, we're going to take our values that we've calculated, and the nice thing about the calculator is it has stored them all for us. We've been recording them on our paper, of course, but they're right here. Stat x bar, that's our mean. I want to hit plus. My t-score, I stored that as t, remember, so I can just press t, times my standard deviation, stat sx, divided by the square root of 20. There is the upper value for my confidence interval. And I can simply go up, press enter, and change this plus to a minus. There's the lower boundary for my confidence interval. So using the calculator to help us with this becomes a very powerful and efficient tool. We don't have to calculate the mean by hand. We don't have to calculate the standard deviation by hand. We don't even have to look up the t-score, our t-value in the table. We can just use the calculator and store everything and perform these nice quick calculations. So what's the answer to our question? Well, our conclusion would be that we're 90% confident that the interval from 292.32 to 320.32 millivolts captures the true mean tension for the entire batch of video terminals produced on that day. So, this is the process that we just went through. Now, using T procedures, we have to use them wisely. We can't always use them. This process, this confidence level, is exactly correct when the population is exactly normal. But most populations aren't exactly normal. They're only approximately normal. The usefulness of the T procedure depends on how strongly they're affected by lack of normality. And this procedure, this inference procedure, is called a robust inference procedure if our calculations remain accurate when a condition for using the procedure is violated. For these T procedures, these are quite robust against non-normality of the population, except when we're dealing with outliers or strong skewness. Large samples improve accuracy of critical values. We know that. And it improves it especially when the population is not normal. So except in the case of small samples, the condition that the data comes from a random sample is more important than the condition that the population is normal. And here are some guidelines for us to follow. If the sample size is less than 15, we use T procedures if the data appears to be close to normal. That is roughly symmetric, single peak, no outliers. We can look at our normal probability plot and make sure that it's linear. If the data are clearly skewed, or if outliers are present, or if our normal probability plot isn't linear, do not use T. If our sample size is at least 15, the T procedures can be used except if we have outliers or strong skewness. And for large samples, for things greater than or equal to 30, T procedures can be used because we're using our central limit theorem. If our sample size is larger than 30, we can use an approximate normal distribution. So here's a summary of everything that we've just run through with estimating our population mean using confidence intervals. Make sure that those summary bullet points, make sure you remember seeing them, make sure they make sense, and if they don't make sense, well, make sure you ask that question that you need to.